So next I want to think about how many subsets can we form from a set with n elements. And so the way that I want to think about this is imagine that you have a set with n elements in it, say 1 through n, it doesn't really matter what they are. And we're going to write down all the elements here. We're going to put them all in a row. So we have n elements. And the way that we're going to form a subset is we're going to go up to the first element and say, are you in this subset or not? And there's going to be two choices. Either it's in the subset or it's not. There's going to be two choices for the second element. Either it's in the subset or it's not, and two choices for all the rest. So it turns out that using this style of argument, there's 2 to the n subsets of a set with n elements in it. So if you have a set of cardinality n, then there's 2 to the n subsets. This is something that we already knew because our notation for a power set, this is really why the notation for the power set is what it is, right? We know that you can go back to chapter 1 and think about a power set, but a power set is the collection of all the subsets of a set E, or whatever you want to call the set. And so the cardinality of a power set is 2 to the cardinality of E. And that's essentially what we just proved in number 5, that if we have a set with n elements, a set of cardinality n, then there's 2 to the n subsets. Okay, so this is why that notation was what it was for the power set before. All right, a WEP key password consists of a sequence of 10, 26, or 56 hexadecimal digits. Hexadecimal means base 16. And we want to know how many such passwords are possible. Well, there's no overlap. So these are disjoint sets. So we can just add how many hexadecimal digits are there that are 10 characters long. And it turns out that if you have a sequence of 10 characters, there's 16 choices for the first character, 16 choices for the second. And so altogether, there's 16 to the 10 hexadecimal, there's 16 to the 10 sequences of hexadecimal digits. There's likewise 16 to the 26 hexadecimal words, for lack of a better term here. And then there's 16 to the 58 sequences of hexadecimal digits. Okay, so that's all there is there. I like to do card problems in this section because cards are a nice way to think about counting. This is a nice way where counting comes up. And so just so that we're all on the same page in terms of cards, a standard deck of cards, which is the only thing that we'll work with over the semester, so everything will be a standard deck, but a standard deck of cards has 4 suits. So there's clubs, diamonds, hearts, and spades. Each suit has a color. So the clubs and the spades are black. The diamonds and the hearts are red. And then each suit also has 13 denominations. So 2, 3, 4, 5, 6, 7, 8, 9, 10, plus a jack, queen, king, and an ace. Typically, the jack, queen, and king are called face cards. The ace is not typically considered a face card. So that'll be relevant for us. I'll repeat that in an example later in this chapter. So we want to know how many cards are aces or jacks. So there we go again with the word jack. So what we have to, with the word or, I mean, so we have to count the number of aces, and there's 4 of them. There's 1 ace per suit, plus the number of cards that are jacks, and there's again 4 of them. And then we want to know how many cards are aces and jacks, and the answer is none of them. Because to be an ace and to be a jack are disjoint properties. There's no card that's an ace and a jack. You can only be one. You can only have one denomination. So it's 4 plus 4 or 8. So there's 8 cards that are aces or jacks. How many cards are clubs or queens? Well, we can do the same count or similar count anyway. So how many cards are clubs? Well, there's 13 clubs. Okay, so we have 52 cards total. Each denomination has each suit has 13 denominations, and so that means that there's 13 clubs. There's 4 queens, so we're going to add 4 to it, except there's a single card that we've counted twice, namely the queen of clubs. So that's a card that was in both piles. So what we're going to do is we subtract it so that we get the proper count. So it turns out that there's really only 16 cards that are relevant for us. So there's 16 cards that are clubs or queens. How many cards are kings or red? So how many kings are there? Well, there's 4 kings. How many red cards are there? Well, there's the diamonds and the hearts. So that's 13 times 2 or 26. And then how many cards are red kings? Well, namely the king of hearts and the king of diamonds. So there's 2 of them. So it turns out altogether there's 28 cards that are kings or red. Okay, so that's how we'll go about doing these card problems. How many positive integers less than or equal to 1,000 are there that are multiples of 3? Okay, so let's start with a little bit of notation. I feel like this example in particular is really missing some notation. So what I'm going to do is I'm going to let a sub n be the cardinality. So let me just write it rather than being formal here. But this is going to be the number of integers. And actually, let me say the number of positive integers. So this will be the number of positive integers that are multiples of n and are less than or equal to 1,000. Okay, so formally what I was going to write before, which I might as well write, this is going to be the number of positive integers x, such that x is a multiple of n, so n divides x, and x is less than or equal to 1,000. So it's the cardinality of that set. Okay, so I'll put the bars there for the cardinality. So how many multiples of 3? Well, that's just the cardinality of A3. And so we want to think about how many multiples of 3 are there from 1 to 1,000. Remember, we're not including 0 because we're only talking about positive integers, and 0 is not positive. So it turns out that there's going to be 333 of them. And the way that you can get that is that it's 1,000 divided by 3, except we're going to take the floor of that. Okay, so if you think about that for a couple seconds, that turns out to be the right way to count how many multiples of 3 are there from 1 to 1,000. So it turns out that there's 333. How many multiples of 4? Well, it turns out there that there's going to be 1,000 over 4, which happens to be 250. And when you take the floor, you still get 250. How many multiples of 3 and 4? We need to think about this. To be a multiple of 3 and 4 means that you're a multiple of 12. The reason why it's 12 is that 12 is the least common multiple of 3 and 4. It is the product, but more to the point, it's the least common multiple of 3 and 4. The reason why the least common multiple of 3 and 4 is the product of 3 and 4 is because 3 and 4 are relatively prime. So here we're going to figure out how many multiples are there of 12 from 1 to 1,000. Okay, and so we need to divide 1,000 by 12 and take the floor of it. And when we take 1,000 and divide it by 12, what we're going to end up with is 83. So there's 83 multiples of 12 between 1 and 1,000. Now, how do we figure out the multiples of 3 or 4? Well, what we would do is we would add up the multiples of 3 plus the multiples of 4 minus the ones that are multiples of 3 and 4. And so this is going to end up being 333 plus 250. So 333 plus 250 minus 83, which will turn out to be exactly 500. Okay, so a nice even number there. So it turns out that half of the numbers from 1 to 1,000 are multiples of 3 or 4. Slightly more tricky, how many integers from 1 to 1,000 are multiples of 3 but not 4? Well, the way that we're going to do this is we're going to think about what does it mean to be a multiple of 3 but not 4. We're going to throw up basically all the numbers except the multiples of 3. So we're only going to work with the 333 integers that we have. 3, 6, 9, 12, 15, and so on. Now, which of those numbers, 3, 6, 9, 12, 15, 18, and so on, are multiples of 4? Those are going to be the ones that we have to throw out. And it turns out that the ones that are multiples of 3 and multiples of 4 are the multiples of 12. So that's the right one that we have to subtract out. So again, if we want to count the multiples of 3 but not 4, we start with the multiples of 3. So we have 18, 21, 24, 27, okay, and so on. And then we want to count the ones that are multiples of 3 but not 4. So that means that we have to throw out the ones that are here. In other words, the ones that are multiples of 3 and multiples of 4. Okay, so 12, 24, and so on. So these are the multiples of 12. So this is the right way to count that. So again, it turns out that there's 250 of those. How many are multiples of 3 or 4, but not both? And this is, again, a slightly trickier way to do this. The way I like to think about this is that we can count this by finding how many are multiples of 3 but not 4. So that's 1,000 over 3 minus 1,000 over 12. Again, taking the floor of each of those quantities. Plus the multiples of 4 but not 3. So it's going to be 1,000 over 4 minus the floor of 1,000 over 12. Or you can think of this as, I think it's just instructive to think of this as the multiples of 3 plus the multiples of 4 minus 2 times the multiples of 12. Okay, and so when we do this, it turns out that there's going to be 417 of these, just assuming that I did that math correctly. So there's 333 plus 250, and then minus 83, minus 83. So yeah, 417 integers from 1 to 1,000 are multiples of 3 or 4, but not both.